Hey everybody, welcome back. This is the beginning of Chapter 11, which is all about nuclear chemistry. So you may think of nuclear chemistry, and at least me, I can't help but think of The Simpsons, and we'll actually be talking about nuclear reactors and fission reactions as we get towards the end of this chapter. So here's what we're going to talk about. We'll talk about stable and unstable nuclides, the nature of radioactive emissions, equations for radioactive decay, the rates of radioactive decay and half-life, transmutation and bombardment reactions, the radioactive decay series, and that's kind of the first half of the chapter. In the second half, we'll talk about the detection of radiation, the chemical effects of radiation, and then the biochemical effects of radiation, sources of radiation, nuclear medicine, fission and fusion reactions, and nuclear and chemical reactions compared. So let's start with section 1, 11.1, stable and unstable nuclides. So our goals in this section are to discuss general terminology and notation associated with nuclear instability, and then to understand the major ramifications associated with nuclear instability. So a nuclear reaction is a reaction where changes occur inside the nucleus of an atom. So this is different than the chemical reactions we've been talking about in class so far, because so far the chemical reactions we've been talking about involve the transfer or sharing of electrons, like making ionic bonds or making new covalent bonds. Whereas with nuclear reactions, instead of electrons being involved in kind of the core feature of the chemical reaction, the changes are happening actually inside the nucleus. So your number of protons is typically changing. So we define a nuclide as an atom with a specific atomic number and atomic mass. And so a nuclide differs from an isotope because an isotope is an atom of the same element with a different mass, whereas nuclides can actually be different elements altogether. So for example, carbon-12 and carbon-13 are isotopes of each other. They're both carbon because they both have 6 protons, but they have different numbers of neutrons, so they have different masses, and we figure out the average mass of an element by taking the weighted average of all of its isotopes. So these are isotopes, they're the same element, but they have different masses. Versus nuclides can be completely different elements. So carbon-12 and oxygen-16 are nuclides. They're just a specific atom with a specific number, atomic number, and atomic mass. So in order to define a nuclide, you have to know both the atomic number and the mass number. So just a quick review of atomic symbols. I think this is all the way back from chapter 1. Your mass number is the total number of protons plus neutrons. That's the larger number that's kind of on the top of the fraction if we're using this fractional notation. And the atomic number on the bottom is the number of protons that the atom has. So all atoms of the same element have the same number of protons. So any atom that has 7 protons is going to always be nitrogen, or any atom that always has 8 protons, for example, is always going to be oxygen. So for isotopes, we didn't necessarily have to know the number of protons, because if we said we were dealing with an isotope of carbon, we would know that because it's carbon, it's always going to have 6. For nuclides, because when we're talking about nuclear reaction and the nuclides involved in the reactions, because in nuclear reactions the number of protons can change, we always for nuclides have to also include the number of protons, because that could be changing throughout the chemical reaction. Something that doesn't change is that still, anytime you have 6 protons, it's a carbon atom. Anytime you have 8 protons, that's an oxygen atom. Anytime you have 7 protons, that's a nitrogen atom. The proton still defines what element we're dealing with. It's just that in a nuclear reaction, you could start the reaction with oxygen and end up with a different element by the time you're done with the reaction. Versus in chemical reactions, due to the law of conservation of mass, the type and number of each atom on the reactants on the product side has to stay the same. We have to have balanced chemical equations in terms of the types of atoms. Not so in nuclear reactions, because the number of protons is going to be changing in a nuclear reaction. Okay, So here's some nuclear chemistry terminology to get us started. Nuclide, this is the first thing. It's an atom with a specific atomic number and atomic mass. And then we have stable and unstable nuclides. So a stable nuclide does not undergo a spontaneous change in the nucleus. So it has a stable nucleus and it won't spontaneously change. Versus an unstable nuclide is a nucleus that will undergo a spontaneous change. Within the category of unstable nuclides, we have what's called a radioactive nuclide, or just a radionuclide. And that's a nuclide with an unstable nucleus from which radiation is spontaneously emitted. And then the term radioactivity refers to the radiation that is spontaneously emitted from an unstable nuclide. So a radioactive nuclide emits radiation, and the radioactivity is the radiation that's emitted from an unstable nuclide. So currently, there's 118 elements currently known. 88 of those occur in nature, and 29 of the naturally occurring elements are radioactive, meaning they have unstable nuclides, unstable nucleus, which emits radiation. So here's some guidelines for how to kind of figure out if an atom or an element is likely to be stable or unstable in terms of its nucleus. So in general, elements that have more protons are less stable. They have less stable nuclei. This is because you're cramming all those protons into a teeny tiny space inside the nucleus. If you remember the size comparison of a nucleus is like the size of a penny inside a professional sized baseball stadium in terms of the size of the nucleus compared to the size of the electron cloud. So you have all these protons crammed inside a teeny tiny nucleus. The protons have a lot of mass. And so there's a lot of energy stored up kind of inside that nucleus with all those positively charged protons squeezed really close together. Remember, like charges kind of repel each other and opposite charges attract. So those protons, when there's a lot of them squeezed together in the nucleus, they're not very stable because there's a lot of positive charges squeezed really close together. So all nuclei that have 84 or more protons are unstable. So what this chart shows here is that if your number of protons is greater than 83, so you have 84 or more, you automatically have an unstable nucleus, which means going to be emitting radiation. If you have 83 or fewer protons, then whether or not the nucleus is unstable depends on the number of protons relative to the number of neutrons. Like how many things do you have crammed inside that teeny tiny nucleus? So if your number of protons is greater than your number of neutrons, you have an unstable nucleus. If your number of protons is significantly smaller than your number of neutrons, you have an unstable nucleus. And if your number of protons is about equal to the number of neutrons, but a little bit less than or equal to, then you have a stable nucleus. So kind of the ratio we can look for is that you can have up to 1.5 neutrons for every proton for the element to be considered stable if it has less than 83 protons altogether. So things to keep in mind in general, the more protons, the more unstable the nucleus becomes. If you have more than 83 protons, so if we check our periodic table, what element that is, if your element polonium and above, going higher in atomic number, polonium is element number 84, then you have an unstable nucleus. And if the atomic number is less than or equal to 83, it depends on kind of the relative amount of protons and neutrons. Most stable if you have a few fewer protons than neutrons. Okay, that's it for 11.1. Next time we'll talk about the nature of radioactive emissions, going over what are called alpha particles, beta particles, and gamma particles. I'll see you then. Thanks.